welcome back to a lecture on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 14 in the series on section 3.6, inverse functions. I'd like to motivate the idea of an inverse of a function by reminding us about canceling operations. If I'm going to do something to x, like add 3 to it, I could cancel this addition of 3 by doing the inverse operation, which is subtracting 3. This would give me instead just x plus 0, where plus 0 is a sort of identity operation. In other words, it doesn't change x. And the important part of that is, of course, that this is just x. So in some sense, we've been able to remove the plus 3 by composing it with a minus 3, which gets rid of them. In a sense, this inverse is going to undo whatever the operation does. If we started with x being something like 9, for example, adding 3 would bring me to 12. But then this 12 is going to need to get brought right back to 9 by some kind of inverse operation, which we can see needs to be minus 3. Now let's express this idea in terms of function notation. Let's let some set of rules be add 3 to my input. And let's let this other set of rules, which I'm using this notation, which implies it is the inverse of this one. We say this is f inverse. Let's let that set of rules be minusing 3 from my input. Now, if we compose these two functions, that is to say, if we plug one into the other, we need to evaluate f at now x minus 3, which will give me x minus 3 plus 3, which is just x. So in composing these two functions, I just get x back. Now we saw that order of composition matters, but in this case it really doesn't, because if I compose in the other direction as well, I still get x plus 3 minus 3, which is just x again. Now the identity in this case of composition of functions isn't really plus 0 anymore. It's more general than that. We call this function that just gives me x back no matter what, the identity function. You plug in an x, it gives you back an x. And it doesn't really do anything to it. X remains identical. The graph of the identity function is just this line. You might know it as y equals x, or having a slope of 1 and a y-intercept of 0. This is actually the function that graphs x and y in identical pairs. Every x and y value along this line are equal to each other. Sort of like the picture that we saw before, function inverses are going to exchange the role of output and input. If my f takes x to some y, then this y is going to get brought by f inverse back to x. Let's just say that they're numbers. If my f brought a to some number b, then f inverse has to take b back to a again. That's what it would mean to undo or do the opposite thing of f. And so we would have that f inverse of b was equal to a. Now this switching of inputs and outputs, of reversing the roles of x and y, is going to look like reflection over our identity line, using this identity line as our axis of reflection when we look at these graphs of f and f inverse. Here's just an example, not using x plus 3 and x minus 3, just some general f and f inverse. And I want you to think about why reflection over this line might have to do with reversing the roles of x and y. Here you can kind of see an example of one. If f goes through minus 1, 1, that is to say, if f takes minus 1 as an input to 1 as an output, then f inverse better take 1 as an input to minus 1 as an output. And you can see that these are reflected over the y equals x line. Another way that you can see that this has to be reflection is to imagine what interchanging the roles of x and y would do for the axes. If I'm on the x-axis, positive x-axis, and I switch with the positive y-axis, I am twisting around this line. And that's going to look like reflection around that line. So now let's consider where this process or this idea of an inverse might start to break down a little bit. Let's say, for example, we have a function like x squared. When we try to cancel things that look like x squared equals 4, we needed a special procedure for that because we seem to get multiple answers to this question of what x's would make this happen. We learned the square root property that says if this is true, then I need to take plus and minus the square root of both sides. And actually, this gives me two answers back. because both -2 and +2 will square to be 4. Now, if we consider the graph, we can see a geometric reason as to why this is. At the horizontal line of 4, right, this hits my graph in two places. The y value of 4 means my x value could be -2 or it could be +2. So something about intersection with this horizontal line has meant that there were multiple inputs that could give me the same output. Having multiple inputs that give me the same output is called being not one-to-one. And we see that the horizontal lines will pass through that curve in more than one spot. This is called failing the horizontal line test. On the other hand, if we could pass a horizontal line through a curve and it only hits that curve once, then we call this passing the horizontal line test, and those that pass are called one-to-one functions. Every y value that the function hits is only hit by a single x value. Let's take a look at that idea of reflection over the identity line and see what that looks like in terms of the horizontal line test. Notice that if I reflect this whole parabola down here, I wind up with sort of two different branches, but taken as a whole, taken as a plus and minus square root of x relation, it fails the vertical line test whenever this one fails the horizontal line test. Interchanging the roles of x and y means interchanging what's a horizontal line with a vertical line. And those that fail the vertical line test are not themselves functions. They're relations or multi-valued maps, but they're not functions themselves. And so if we're looking for an inverse function of this curve x squared, we need look no further. We won't find one. Not for the entire curve anyway. We could consider one branch of the curve at a time. We could either consider this negative branch or this positive branch. And those separate branches across these separate restricted domains, they could have a function inverse. If I restrict just to the positive numbers, then I would just take the positive square root. But if I knew that I was looking at a negative number squared, if I wanted to find out what that was, I could take the negative square root. We'll talk more about this domain restriction presently. For the meantime, just try to keep in mind that there's something important to distinguish about a function being one-to-one or not, and whether or not it has a function inverse. If a function asks, what is y given x, then its inverse is going to ask, what is x given y? And if a function isn't one-to-one, that second question is going to have multiple answers. And putting one input in, asking one question, and getting multiple answers back, we talked about how that is not a function. So we're going to want to be careful in those cases. So now let's start to go through these guided notes. To decide which of these are one-to-one functions, we want to see which ones pass the horizontal line test. Well, I have a horizontal line right here. If I pass it through this first function, it does only appear to hit it in one spot. So that first one passes. This line, only hitting it in one spot, it passes. This circle, hitting it in two spots in many places, so that one fails the horizontal line test. Here I've got a parabola, that hits it in two spots, that's going to fail. And this one here, this one, though it zigs and zags, it seems like it only hits it in one spot, so this one passes. And here we have this wiggly function here. When I pass it below a peak, it's hitting it in these two spots, or near a valley, it's hitting it in these two spots. Actually, it seems to keep hitting it over and over again, so this one really fails the horizontal line test. So just to recap, the answer to the question, does every horizontal line hit this function or this relation in more than one spot, has the following answers. Question 2 is actually asking the same question, because those functions that possess an inverse function are exactly those that pass the horizontal line test. So let's try it again. This one, horizontal line, hits it in one spot. Horizontal line hits it in one spot. The horizontal line seems to be hitting it in one spot, although there's not very much function here for me to look at. Here, doesn't hit it in one spot, hits it in a couple spots. That's no good. Here I'm hitting it in one spot, it would seem. Yes. And here I'm hitting it in several places, 2, 3 spots, possibly more, depending if this continues. So we wind up with the following answers to the question of whether or not these functions are invertible. I want you to notice that in mathematics, oftentimes knowing just a little bit about what these highly technical terminologies means answering the question in a pretty simple way. Here, if you don't know what invertible or an inverse function means, it sounds quite intimidating. But if you just look and see which of these are hit in only one place by a horizontal line, that's something that your brain can figure out pretty intuitively. And so just knowing a little bit about the terminology sometimes turns a daunting problem into a fairly simple problem. So here we're looking at tables of values. You could plot these points and see which ones get hit by a horizontal line, but what we're really looking for here is repetition of a y value. I have two inputs here, different inputs, which give me the same output, and such a function is not one-to-one. Likewise here, same issue. Here I see no repetition of values, right? All the y's are distinct values for distinct values of x. And the same for this last one here, distinct values of x gave me distinct values of y, and so this one is also a one-to-one function. Notice how similar this exercise is to comparing whether or not something is a function or just a relation, where we were looking for repetition of x values giving a distinct y value. In fact, that exercise is featured right here because this is not a function. If identical x values give two outputs for y, then this fails the vertical line test, and we don't have a function, we have a relation or a multi-valued map. This one here has distinct x's, distinct y's, so this is a one-to-one function. This one here has two outputs of y which are the same for two different inputs of x, and so this one is not one-to-one. It is a function, but it's not one-to-one and wouldn't have a function inverse. Question 5 is the same. It's just giving us the information in a coordinate list instead of in a table. So we need to look first of all to see if each one is a function by checking for repeating x values. And then we check to see if it's one-to-one. If it has repeating y values, it's not a one-to-one function. If it has repeating x values, it's not even a function. So here we have x values 5, -1, -4, 2, 7, 3, -3, no repetition there. And what about our y values? -2, -6, 5, -3, -9, and +6. So this one has no repetition of x or y. It is a one-to-one function. Likewise with this one, we got -5, 0, 1, 4, 8, and 12. None of those repeat for x, so it's a function. -3, 0, 3, 5, 7, and 13. None of those repeat for y, so this is a one-to-one function. Next one, 9, 3, 4, 2, -4, and 10. So those don't repeat at all for my x values, but the y values, 1 and 1, okay, so these two repeat. That's a problem. And 0 and 0, these two repeat. So this is going to cause us a problem, right? The repetition of these means that it's not one-to-one. If the y values repeat, it's not one-to-one. Checking through this next line, -5, 1, 6, 9, 11, and 14, all the x values are distinct, so it's a function. And the y values, -3, 2, 4, 8, 12, and 16, those are all distinct, so this is a one-to-one function. Again, we've got to check for x value repeating. Oh, wait a minute, I see one. So here I have 3 and 3, giving me two distinct y value outputs. This is in fact not a function. All right, moving on. For this one, we're given a function which is not one-to-one. And what they want is for us to restrict the domain or only look at part of the function, the biggest possible part over which it is actually one-to-one. So we want no repeated values in y. Notice that what we're looking at with this function is an area on which it is decreasing, right? And so has distinct y values because they're always changing by going down. But then all of a sudden, it sort of like reverses course and starts heading back up again. And it was precisely this turn, this pivot from increasing to decreasing, that meant that we had to have a region in here where we were hitting multiple x values for the same y value. So what we sort of want to do is omit this peak. I want to cut the function in half so that I'm only looking at either the increasing or decreasing part respectively. So I could choose to look at just the left half of the graph. That is to say, just look at the negative values. We could go from -infinity up to 0. And what they mean by of maximum size is just that you wouldn't want to take a proper subset of that. That is one-to-one in this region, but we could do better. We could get bigger and include more and still have it be one-to-one. Or correspondingly, you could take the other half of the graph where it's increasing and just look at that domain, in which case you're just looking at the green branch here of the function where it's also just 1 to 1. There are no repeated x values for any given y value, and that would be this interval here. So either of these two intervals are acceptable answers over what is a domain of maximum size over which it is 1 to 1. The next question asks us to determine if the graphs of two functions represent a pair of inverse functions. And the idea behind this one is just to look to see whether or not they are actually reflections around the identity line. It helps then to maybe plot the identity line. Now, although they do seem to be having some kind of line of symmetry, all intersecting lines do that. So what we really want to say is, does it look like reflection over this line? And we can see that that's not true. The point of intersection is off the line. If two lines are going to intersect and also have a symmetry about y equals x, they're going to need to intersect on that line. That's just a property of reflection. We can see then that these do not represent a pair of inverse functions because they do not show us reflection over the line y equals x. Something like this would be the reflection of this line. Something like that would be the reflection of that line. So no, they are in fact not reflections over the y equals x line, so they are not a pair of inverse functions. The same thing is true here. They're asking us to see if these are reflections around the y equals x line, and we can even more easily, I think, see that they are not. Here's the y equals x line again, right? Are these inverses over that? Are they reflections over that? And the answer is no, they are not. Right, just looking at this region here, I think we can see that these are clearly not reflections over that line, and so we can rule them out as being inverses of one another. Here we're asked to actually sketch the inverse of this function. Let's first plot the identity line. That would look like this. And let's find a couple points on this graph that we could reflect. For example, here I can see a point, and here I can see a point where it clearly passes through two integer values for x's and y's. So what I can do is reflect that. Instead of going through 0, -2, I'll go through -2, 0. Instead of going through 3, 0, I can go through 0, 3. And now if I just connect those two lines, we can see that this has a slope of positive 3/2. And so we go down 3 over 2, down 3 over 2. And we extend this line over 2 up 3. And there we have it. And this shows a nice reflection over the line y equals x. Here's another one. We're asked to sketch this graph over the identity line. So let's plot the identity line first. And then we want to interchange the role of x and y. So here we have what looks like -6, -1. So we want to do -1, -6, and put an open circle there. And what's another point that it looks like this goes through? Kind of looks like it goes through -8, 1. So let's go to 1, -8. And that'll help guide our curve. Another point it looks like it goes through is -10, 7. So if I go to 7, -10, and I put a dot here, that'll help guide my curve. And now let's just try to connect these points smoothly. And there we have drawn the reflection of this graph over the y equals x line, so we have drawn the graph of its inverse. Same drill, we draw the y equals x line, and function inverses switching the role of x and y means that I should switch the role of x and y in each of these points. So here I have a point -4, 5. So if I go to 5, -4, I'm going to want to put my point there. It's an open circle. Then I'm going to want to look at -1, 1. So we go to 1, -1, and we put a point there. And those two are connected to each other, so let's connect them now. Then we go to 4, -2. So if I go to -2, 4, and put a point, these two are connected. So let's connect them now. And then the last point is at 6, -5. So if I go to -5, 6, and I put this point here, and we connect them, and we have indeed drawn the reflection of this graph over the y equals x line. So these next questions are asking us to test whether or not two things are inverses of each other by composing them. And the idea is that when we compose a function and its inverse, we should just wind up with x. If you compose two things and you get an x, if you compose them both ways, I should say, and you get an x, then you are looking at a inverse function. But here, I don't think we're going to have any such luck. Really what we're doing is plugging in x plus 1 into this function, which says add 15 to my input. So I'm adding plus 1 and then I'm adding plus 15. That's just the same as adding 16. That's not just x at all. So no, it's not an input. Let's finish the question though by answering what is g of f of x? Well, this is going to be f of x, g of x plus 15 then. G says add 1 to my input, so I take x plus 15 and I add 1 to that. And although these two do match, they do match, but they're not the identity function. So these aren't inverses of each other. So for this next one, we're going to want to compose the two functions again. What is f of g of x? Well, we need to take g's rules and plug it into f of x. So we take f of x plus 4 divided by 5. And then f's rules say multiply that by negative 5 and then add 7 to it. And we were doing pretty good with this times minus 5 because that cancels. But now I just wind up with x plus 4 plus 7. And that's just x plus 11. That's not the identity function. These are not function inverses. On the other hand, we could also look at g of f of x, which is to say take g of minus 5x plus 7. And if we do that, we're going to want to take the thing, minus 5x plus 7, and we're going to want to add 4 to that and divide it by minus 5. But that's just going to be minus 5x plus 11 over minus 5. And here we can see that not only do we have this problem with this 11, but we're dividing it by minus 5 still. So even though we could cancel this part, we're still going to have minus 11 over 5. So these aren't equal either, but most importantly, their composition is not the identity function, and so they are not function inverses. This one's nice because we're given a restricted domain on this function x squared minus 1, and so we know how to choose when we do inverses of this, whether or not x is going to be positive or not. When we're talking about this guy, we're saying x is positive. So f of g of x is going to look like f composed with the square root of x plus 1, and this is going to give me the square root of x plus 1 squared minus 1. Now, squaring this square root, we're going to drop the square root, and we get x plus 1 minus 1, and that just gives me an x. So we're doing pretty good. Then if I do g of f of x, this is going to be g of x squared minus 1, which gives me the square root. These are the rules of g now, with x replaced with x squared minus 1 plus 1. The plus 1 minus 1 cancels, and we get the square root of x squared. Now, this is normally not something we could necessarily cancel unless we knew that x was positive. If we know that x is positive, then this definitely cancels to x. And thus, g is an inverse of f of x. So here we have the first one. We're actually given a function and then asked to determine its inverse, and then we're going to graph it. Let's introduce the idea of how one can find a function inverse. So what we should do is we should use our dependent variable notation again to say that f of x being equal to x plus 4, my output y is going to be gotten by an input added with 4. And what we want to do now is switch the roles of output and input. We switch the roles of x and y by replacing all of my y's with an x and all of my x's with a y. We want to switch around what x and y are doing in the equation. Now we just want to solve for y. So we take and we minus 4 from both sides in order to solve for y. And that gives us x minus 4 is equal to y. This is our inverse function. So we have f inverse is given by x minus 4. Let's graph all these together and see how that pans out. So here's my y equals x line, 45-degree diagonal there. And then let's plot the line they gave us, which was f of x equals x plus 4. So that's a line with a slope of 1 and a y-intercept of 4. And now let's graph the inverse of that, which is x minus 4. So all these lines have a slope of positive 1, which makes them look all parallel and such, but at the very least we can see that the inverse and the function are reflections over the y equals x line. So here we have another one. Let's take and set this equal to y equals x cubed minus 3. Now we want to take and interchange the roles of x and y. So we write a x here and then a y cubed minus 3. And now we want to solve this equation for y. We do the inverse operations, lowest to highest order first, so we want to get rid of this minus 3 by plussing 3 to both sides. And then we want to get rid of the x cubed by taking the cube root of both sides, or the 1/3 power. And this is now going to be my inverse function. So let's graph those two things and the identity line. Let's start with the identity line. And now let's address the cube. So our first function was the cube power, right? The third power downshifted by 3. So we want to use our function transformations here. That's going to take what normally would be at 0, 0 down by 3 units. If you go over 1, the cube of that is 1. If you go over another 2, the cube of that would be 8. And so downshifted by 3 would bring us to 5. We can't fit any more cubes on here because the cube of 3 is 27, and even downshifted by 3, that's 24. That's well off the edge of our map. So let's just connect these and show that it gets steeper, something like that. Now, the cube of minus 1 is minus 1, and then downshifted by 3 brings us to minus 4. And then the cube of minus 2 is minus 8. Downshifted by 3 brings us to minus 11. So here is a graph of our cubic function, f. Now let's graph its inverse. Notice that the inverse hasn't been downshifted, it's been left shifted by 3 units. So we want to take the cube root function and left shift it by 3 units. But, well, we have these points that we plotted for the regular function. Let's just take and invert those or reflect those over the y equals x line by switching the roles of x and y. So if the cube function is going to go through 2, 5, for example, then our inverse is going to go through 5, 2. Likewise, if it goes through 1, negative 2, this is going to go through negative 2, 1. Or 0, negative 3 goes through negative 3, 0. Or negative 1, negative 4 goes through negative 4, negative 1. And by the way, you could plug some of these in. Like, these are just values that will evaluate nice inside the cube, right? If you plug in negative 4, right, you get minus 1, and the cube root of that is minus 1. If I plug in minus 11 in here, minus 11 plus 3 is negative 8. And the cube root of negative 8 is negative 2. And now let's connect these dots, something like that. And that's our inverse function. And we can see that despite the kind of sloppiness of my graph here, they are in fact reflections over the y equals x line. And so here we have a similar exercise. We want to take f of x being equal to x minus 6 to the third power minus 5, and we want to invert it. So we begin by using dependent variable notation and setting y is equal to the cube of x minus 6 minus 5. Then we switch the roles of x and y, because that's what inverses do. Then we want to solve for y again. So we want to add 5 over to this side. Then we want to take the cube root to get rid of this cube. Then we want to take and add 6. Now we can use function transformations to see what's happened here. We had originally a function which was right shifted by 6 and downshifted by 5 and was cubic in nature. Now we have one that's cube root in nature and has been left shifted by 5 and up shifted by 6. So let's see if that all makes sense when we graph this. We begin with the graph of the identity line. Now we can graph our cubic function by using function transformations and a few points from the cube. We're going to want to go right by 6 units and down by 5 units, which brings what was at my origin here. Normally, if I plug in 1 into the cube, I get 1, but that's now also going to be right shifted by 6 and down shifted by 5. Or, you could plug in points around this point, like plugging in 7 would give me a 1 here, which cubed is 1, and then downshifted would give me minus 4. Or we can sort of just start to trace out some of the known points around that cubic. Over 2 up 8, for example, bring me to 3. Over 2 down 8, for example, brings me off the edge of the map. So let's just draw these points on the cubic, something like that. is my f of x. And now the inverse of that is the cube root function, which looks like this twisted and laid on its side. And that's going to be over left 5 up 6. So what normally would have gone through the origin is left 5 up 6. And notice we have this mirroring of points at 6 minus 5. Now we're at minus 5, 6. What was at 7 minus 4 will now be at minus 4, 7. What was 8, 3 will now be at 3, 8. And what was at 5 minus 6 will now be at minus 6, 5. And so we can try to connect these dots, more or less. This is our inverse function. And we can see that they are indeed reflections over the y equals x line, so we have good indication that we've done this properly. Here we have yet another cubic, or this one's a cube root, and we're going to find its inverse, which is going to be a cubic. If we start with f of x equal to the cube root of x plus 5 minus 8, we want to write this in dependent variable notation to make things a little bit easier to switch. We want to switch the roles of x and y. We want to solve now for y. Adding 8 to both sides, we isolate the cube root. Then cubing both sides, we cancel it. And now we want to minus 5 over to get y. This means my inverse function is x plus 8 cubed minus 5. I think it might be easier to graph this inverse function first, so let's do that. There's no reason not to. We are now left shifted by 8, down shifted by 5. So we go left 8, down 5, and we put our mark, because the original cube root passes through the origin. So now what? Well, now what would normally have gone over 1, up 1 is going to go over 1, up 1 here, or left 1, down 1, or over 2, up 8. Up 8 would bring me from minus 5 to 3. Down 8 would bring me from minus 6 to minus 12. So those are some points from the original cubic. Alternatively, you could plot points around here, right, by plugging in values around minus 8 and seeing what you get. Connecting the dots, we get something that looks approximately like this. And as we mentioned, this is our inverse function. Now let's flip those points to graph the original function, the cube root. So this is going to put my minus 10 minus 12 at minus 12 minus 10, which is here. Then we're going to have minus 9 minus 6, go to minus 6 minus 9, which is here. Negative 8, negative 5 goes to negative 5, negative 8. Negative 7, negative 4 goes to negative 4, negative 7. Negative 6, 3 goes to 3, negative 6. And we complete our graph by connecting these dots. And this was the original cube root function. For this next one, we're asked to find the inverse and then evaluate it at a point. Again, we want to rewrite things with y notation here, switch the role of x and y, and now solve for y. We begin by missing that 5 over to the other side. We want to multiply on both sides by y plus 1. Then we want to divide off this extra x minus 5 term. And finally, subtract 1 from that. This gives me my inverse function, which we can now evaluate just by plugging in 6 to get 2. For 28, we're asked to look at a restricted function. It says the function indicated by x minus 4 squared minus 3 is not 1-to-1, and so does not have a function inverse. However, the domain restricted to 4 to infinity, as shown below, is 1-to-1. Now, can we graph it, determine the inverse as a formula, and so on? Okay. So here what I want to do is take the function notation, rewrite things involving y, and switching the role of x and y, I now want to solve for y. We add 3 to both sides, we get rid of this square by square rooting, and then we get rid of the minus 4 by bringing it over as a plus 4. This is my inverse function. Let's sketch the identity function first, and now let's sketch this function. Notice that this point here, the vertex of the parabola, is going to be switched in the roles of 4 and minus 3. So we go to minus 3, 4, and plot an open circle. And that accords with the idea that we have left shifted by 3, the square root function, and then up shifted it by 4. Just like this one goes through this point here at 5 minus 2, we're going to go through minus 2, 5. Instead of going through 6 and 1, we're going to go through 1, 6. Instead of going through 7 and 6, we're going to go through 6, 7. And I think that's enough points to sort of sketch out this square root function. And we can see that aside from my artistic license, it looks like a reflection over the y equals x line. The restricted domain that they gave us for the original function was from 4 to infinity. Actually, they used an open circle, so let's say this is from 4 to infinity. Although I couldn't help but notice here that they actually restricted the domain to a bracketed function here, so I consider that to be a bit of a discrepancy. This graph should be a filled-in circle if this is to be truly the domain. So watch out for that in this question. When you answer something like this, I'm unsure about whether or not we're supposed to input a domain that comes from this graph, which seems to indicate an open parentheses here, or if we're supposed to use the prompt of the problem, which actually says that this is supposed to be a bracket. I'm actually going to use the bracket because there's no reason why we couldn't include this point. It's still one-to-one if we do, and so that's part of the maximum restricted domain. Interesting that they chose this open circle here. I do not understand that. Okay, so what's its range? I'm going to use the bracketed version of this question. Well, it's going to go from -3 up. So this is from -3 up to infinity. And what is the domain of f inverse? Well, that's going to start at -3 and go up to infinity. And what is its range? Well, its y values start at +4 and go up to infinity. And perhaps you notice this correspondence, that these two are equal and that these two are equal. And that's just about this idea of exchanging x and y values again, right? If the function takes x's to y's, then the inverse function takes them back again. We've interchanged the roles of x and y, and so we've interchanged the roles of domain and range. In general, the domain of a function will be equal to the range of its inverse. And vice versa, the range of a function will be equal to the domain of its inverse, which is a nice fact to keep in mind. Okay, here we have a rational function and we want to find its inverse. This can be done whenever we have two lines that are divided by each other. It becomes quite a bit more difficult if we increase the degree of the polynomial, but for right now, let's just follow the instructions as we've been following them. I want to take f of x equal to x minus 1 over x minus 6, and I want to rewrite this involving y's first of all. Then I want to switch the role of x and y. Now that's going to mean replacing all of these x's with y's. Now we want to solve for y, but there's so many of them. We have to clear denominators first by multiplying this denominator on both sides, which brings it over to this side. And now we need to get the y's together, and they're very much separated here. So what we need to do is distribute the x into both terms. And this gives me xy minus x times 6 is equal to y minus 1. Now we're going to move those terms that have a y over to one side. So that would mean minusing y here from both sides. And we're going to want to move these terms that do not have a y, that means the 6x here, I'm going to want to move that to the other side, which gives me the following line. So now I'm going to want to factor out a y, and then divide that off to the other side, which finishes the problem and gives me my inverse function. Once we have that inverse function, we can evaluate it at whatever point we like. So plugging in -10, for example, I wind up with -61 over -11, which is just 61/11ths. To finish this problem, we're asked to use the information about domain and range that we talked about in the last problem, that taking an inverse interchanges the roles of domain and range. So if the domain of this first function, f, was -infinity to -6 unioned with 6 to infinity, that's going to be the range of our new function. The range of the inverse is the domain of the original function, and likewise the range of the original function is the domain of its inverse. So we just switch their roles and copy them down. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.